Alright, welcome to another AQA A-level chemistry video. Today I'm going to be doing a video on proteins. So I'm making this video, it's not going to be too over the top. I'm going to be talking about synthesis of proteins, different types of structures, different use of different types of proteins or why they're useful, shape. But the main reason I did this video is because I wanted to say in every bit of detail that you should know, and that's because people do this. Questions that is simple. Everyone pretty much knows about proteins, right? Everyone knows about proteins. For the area of chemistry or biology. Obviously, this is a chemistry video, but I guess it can, in a way, kind of apply to biology in it as well, because everyone, when answering questions about proteins, everyone forgets to mention the things that they know. Things like mentioning that proteins are made from monomers known as amino acids, and they join together by peptide bonds or strong covalent amide bonds to form the polypeptide chain. They mention the fact that it's got amino. They mention they're made from. They got primary structure, secondary, tertiary, but they forget to mention what the primary, how they're made, what they're made from, and it's a polypeptide chain, right? They forget to mention where it came from, what the units are, the singular units, which are the amino acids, the properties of amino acids, and then how they can bind together, type of bonding, and then saying that's the primary structure, and then going in more detail. So I'm just gonna stop rambling now and just go straight into the video now. But hopefully, you take that into mind when you answer questions about proteins. All right, so amino acids are monomers that form proteins. Proteins are important biological molecules with complex 3D structures. So synthesis. So amino acids undergo condensation reactions to form proteins. The carboxylic acid and amine groups can react to form peptide linkages. The biological word for an amide linkage, really. So in chemistry, we know this is as an amide bond here, but we know this bond here to be an amide bond, but in biology they call it a peptide linkage, which is fine, but just that you don't get confused between the two. So 2 amino acid groups will react to form a dipeptide. 3 amino acid groups will form a tripeptide, and so on and so on and so on. You get that point there. So this is what it's going to look like. So here you have 2 amino acids. General formula for each amino acids: your R group, your amino group, your carboxyl group. Obviously the hydrogen isn't going to be represented here because it's a skeletal formula, but you know that it's going to be a hydrogen group here. Yes, it'll be on it'll be on this carbonate. There'll be a hydrogen there. Obviously because of 1, 2, 3, 4. But you could know about the base structure of amino acids. We know that it's a nucleophilic addition elimination reaction, which is the condensation reaction that produces the amide bond between the carboxyl group of one amino acid and the amine group of another amino acid, and that forms, this is here between, because this is between 2 amino acids and only 2 amino acids only, we call this simply a dipeptide. And this is a very basic structure of the dipeptide. This is technically just it's not a polypeptide. This is not a polypeptide. So I'm not going to go and talk about primary structure and all that, but this is just a dipeptide. And obviously if it was bonded to another one here, tripeptide, so on, so on, so on. But hopefully you get this just basic point. You should know this by now at A-level chemistry. Alright, so primary structure. So the primary structure is given by the sequence of amino acids. The primary structure is held together by strong covalent bonds with peptide linkages happening between the amino acid units. So in biology notation, each amino acid is represented by a 3-letter code. For example, alanine is ALA, glycine I believe is GLY, methionine is MET I believe, but you don't need to know about that. That's just more of a biology thing. So if you ever see that in chemistry, where they show it represents like ALA, it's just how biologists usually represent amino acids. They're represented by a 3-letter code. But more importantly, the primary structure, as I said before, is given by the sequence of amino acids. Oh, forgot to turn this off. I always forget. It wouldn't be a video of mine if I didn't forget to put on Do Not Disturb mode, isn't it? Yeah, but the pyramid structure is just the simple sequence of amino acids. So this here will be obviously this is an example of a dipeptide, but if we made this into a repeating unit of constant amino acids, obviously the R groups would be different for different amino acids. But as it is right now, just with only the let me just get this highlight this part here. If we're talking about only this, I don't like using this. If we're talking about only this strong covalent peptide link here, which is the main part of the, or I guess it's the main. What would I call it? The functional group? No, I wouldn't call it the functional group of protein, because protein it would be the carbox group. But the main important bond, the peptide link as they call it, or the amide link, here the CONH. That's the only notable bond between amino acids. When you're talking about the primary structure, there's no hydrogen bonding or anything else. People forget about the primary structure. People are always so jumpy to talk about. As I said before, I said in the introduction, people love talking about the tertiary structure, the secondary structure, and they talk about all different types of bonding, all different types of intermolecular bonding, but they forget to mention the most important type of bonding when it comes to polypeptides or primary structure or proteins in general. The most important bond in proteins is the amide bond. So make sure to mention that there's a strong covalent amide bond, and make sure to mention that one of the most important structures, which is the primary structure, which is just the sequence of amino acids, or usually given as you can also call it in chemistry you can call it the polypeptide chain. Yeah. Secondary structure. So the secondary structure is a result of the arrangement of polypeptide chains, which causes a specific hydrogen bonding interaction and leads to a specific secondary structure. There are two types of secondary structure. So I'll get back to here first, but the most important part when you start talking about the secondary structure now, the secondary structure is, so you still have this, you still have your primary structure, but now the way that the now between it can be on the same. If we're talking about there's two types. Okay, first of all, there's two types there's two types of secondary structures. I will go through them, but it's about now that there's hydrogen bonding, so it'll be between the electronegative oxygen atom, or from this oxygen atom here, and then from the electronegative nitrogen atom and partially positive hydrogen atoms, and that will cause hydrogen bonding between other amines, other carboxyl groups, and that causes it to twist or to form a certain type of structure. And this will be between either other carboxyl or other amines on the same polypeptide chain, on a different amino acid on the same polypeptide chain. So just like if we're talking about here, right? So say this is one amino acid here, and this is another amino acid here, and then the amine group here has a hydrogen bonding with a hydrogen here on this hydroxyl group here, right? There'll be attraction between here and here. So say it's like we have many amino acids here. It could be possible that it forms hydrogen bonding with an element on, sorry, with a group on this in particular amino acid. And when it does that, there's two sort of structures that we'll go through. So first of all, the first type of structure that you're gonna encounter is the alpha helix. So the alpha helix is a regular coiled configuration held together by hydrogen bonding, and the chain twists into a coiled helix shape. So you can see here, right? So you have more than one amino acid chain. So if I could separate them out, like, oh, I don't want to use that one. I can separate them out so you can clearly see where the amino acid chains are, right? But the most important thing here, right? The most important thing you need to understand, actually, that's probably from. I've probably messed up a bit. Yes. Right. Cool. Yeah. So yeah, here we go. So you can clearly see here that these are separate amino acids here. I've kind of tried to separate them out to make it a bit more clear for you to see where they are. But as you can see, there's different hydrogen bonding between different amino. So there's hydrogen bonding between different amino acids, and that causes it to twist into a certain shape because of the hydrogen bonding. The hydrogen bonding is causing, it's causing it. So if I've got, maybe I should get a wire, right? If I had an amino acid here, because that hydrogen bonding is causing it to twist and to turn into this alpha helix here, and that's what's causing it to have the shape. The bonding is what causes the shape. And I know people know this, but the way that people word it sometimes is people make it sound like because of the bending, because of the shape, that's what causes the bond. And I know people know that, but people have to be very careful about the way that they word it, because it makes it sound like it's because the way people write it down, it makes it sound like because of the alpha helix shape, because sorry there's hydrogen bonding in the way they'll probably word it is something on the lines of an alpha helix is a coiled shape that allows for hydrogen bonding, and it's not. I've seen some people make that mistake, say because of the coiled shape it allows for the bonding to happen. No, it's because of the bonding that causes the shape to be in that way. I know I'm kind of rambling on here, but just to make it abundantly clear, because I always like to make it abundantly clear, right? Think of it like a rope. Think of it like a rope, right? If I was on here, right, I need to attach this to here, and I put a rope between here, a tight rope between these two parts here, and it caused that, right? And that's what a bond does. That's what the bond is doing to the structure. It's like a tight rope tying two different parts of the chain, causing it to be in that shape. And that's what allows, and that's what, in this in particular, it causes this kind of alpha helix shape here. Hopefully people kind of got my point there. Try to make it as obvious as possible. But that's what's happening here. And you can see there's multiple hydrogen bonds, and that's what causes this shape here. Now the other structure is called the second type of secondary structure is a beta pleated sheet. Beta pleated sheet causes the amino acid sequence to run parallel to one another and extends to give a structure with a pleated sheet. So here I've got two examples. So here's the alpha helix here, and this is the beta pleated sheet. So here, with the two differences between an alpha helix and a beta pleated sheet, is that the alpha helix is hydrogen bonding between different amino acids on the same polypeptide chain, but here it's hydrogen bonding between two different amino acids on two different polypeptide chains, if that makes it clear here, and they run parallel to each other. Now the example that I actually have here is I don't want to I only say this because my chemistry told me about this, and I never really thought about it until he told me about this. Shout out to Dr. Bakari. But this is an example of keratin. What is keratin? Keratin is a protein that's in your hair, and if you always wanted, and you probably never really wanted to buy it, but why is it that some people have different types of hair? Like, not talking about like the color. Obviously the color is pretty obvious, but I'm talking about colors to do with genes and all that, unless you dye your hair, of course. But I'm talking about the way that your hair is. Like, some people's hair are straight, some people's hairs are frizzy, and I promise there is a point to this, and it relates to this. But for example, I'm just gonna say how it is. I could say it, I'm black, so black people's hairs tend to be more frizzy, more curled, more densely packed, and that's more to do. It's more to do a bit more of a. It's slightly more to do with what I'm going to talk about later on, but it's kind of related to this as well. Or it has definitely a bit to do with this, but there's a bit more to it. But why is it that, for example, Caucasian hairs are quite straight, silky hair, not really lots of curls, not as condensed, more free flowing, whereas generally African or black people's hairs are usually more curled and twisted, and it's because the keratin hair, there's less of the height. There's either more beta pleated sheets, or there's less hydrogen bonding. So if with for example, if we're talking just about hydrogen bonding, there's the other examples. That's why I want to keep going back later on. But if we're talking about just hydrogen bonding, let's say it's only hydrogen bonding, right? There's only a secondary structure of keratin, right? Black people would have more hydrogen bonds between the amino acid chain, because that's what keratin is. Your hair is an example of protein, right? But yeah, but if, so for example, black people's hair would be more like this because it'd be more hydrogen bonding between the amino acid chains, and that's why your hair is more curled, more dense compared to Caucasian people's hairs. That they have less hydrogen bonding. If we're talking about just, as I said before, if we're talking about just about hydrogen bonding, they have less hydrogen bonding here, and it'll probably be in a beta pleated sheet rather than alpha helix, and that's why it's less. It's less. They're less densely packed and they're more free flowing. So that's why you need to understand. The point is not about hair. The point is about understanding the structure of these, and what the structure enables. Because in an exam, they're not going to just ask you about the differences. Just they probably would, but they always, you know how AQA like to do things. They like to always add some random example saying a student did this and this, and what they'll really ask you here is, do you understand what the structure is? They'll give you some random example. They might try to throw you off, but it's about understanding what they're trying to. They're just trying to make sure that you understand what the structure of a protein is, and because of the structure, it enables certain visible features. All right, I'll stop talking about that now. But tertiary structure. So, the helices and sheets in the secondary structure can fold and interact to order the polypeptide strands into the final shape of the protein. So the complex 3D shape is stabilized by the following interactions of the amino acid side chains. So disulfide bridges. I'll go into this here, right? So, oh, that's nearly about to fall over actually, and probably have that back here a little bit. Hopefully that doesn't ruin. Nope, we're still good. Right, so keep it like that. No, that's too much. Here we go. Right. So what I was talking about here is that so with the tertiary structure, it's like the secondary structure can form more bonds, and the reason why it doesn't talk about it here, but the reason why the secondary structure can form more bonds, and that's what takes it from the secondary to tertiary structure. Tertiary structure is because these R groups here. Now they don't mention it, but you know that R groups, different types of R groups have different types of elements in them. So sulfur, nitrogen, carbon, and you know that sulfur, nitrogen, carbon can form many different types of bonds depending on what you have. So you can have one type of bond is disulfide bridges. So disulfide bridges are between are strong covalent bonds between sulfur atoms. So if there's two sulfur atoms if there's a sulfur atom on one amino acid's R group and another sulfur atom on another amino acid's R group, then they can form a disulfide bridge. Example of this is probably cysteine and methionine are the two amino acids that I know that have sulfur in their R group. I only know methionine is a starter amino acid. But they can also have weak van der Waals intermolecular forces. That's another one. Hydrogen bonding we know, and then another one is ionic interactions. Now I say the people that do biology already know this already, but one thing you need to get clear is called ionic interactions. The reason why is because they're not strong enough to be called ionic bonds. They're weak. They are technically they're more like ionic charges, distributions of charge where they're like more like partial charges in a way. I wouldn't go as far as saying that they're full ionic bonds. Now in the mark schemes, I think they generally allow ionic bonds, but they wouldn't. I wouldn't. When we think about ionic bonds, we're thinking strong difference in not different electronegativity. We have two oppositely charged atoms that are strong, that form a strong ionic bond, right? That's what we think about ionic bonding. But here is that we have a partially negative and a partially positive, and because of that they technically attract, but they're not. But that's not really a proper ionic bond. It's more of an ionic interaction, very easy to break. But they are there, and it's one of the bonds that you can talk about in the tertiary structure. But I just wanted to make sure that people don't say. Clear it with your teacher. Make sure to look at the mark scheme first, because the mark scheme might just say ionic bonds is the only answer that you give. So I don't want to just tell you something that's wrong. But technically, ionic bonds isn't the right way of saying it. It's ionic interactions. And yeah, and I said before, because of now all these ones I've now mentioned, disulfide bridges. So this here is mostly kind of like they're 3D, but they're very basic 3D compounds. When I was talking about the secondary structure, these are very basic 3D structures. But now that you have these more these more bonds now that you have now that are enabled from the different types of R groups, disulfide bridges, weak van valence molecular forces, hydrogen bonding, ionic interactions, that turns it into a more complex 3D shape, stabilized by the following interactions. What is it? So now we have a more complex, it's more twisted into it. Best way I can just say it is you can get this now, and people look at this randomly, but there is, there are people, pharmaceutical scientists that can know what the shape is, because or not saying this, pharmaceutical scientists, they study this a lot. This is, to you, this may look like a random shape, and I guess technically it is a random shape because I just scribbled it on the screen right now. But the point being that there's a lot of this between all these bonds here. They can work out, because which bonds are more polar, the arrangement of it, and it's very easy to calculate or work out what the structure is by doing different types of techniques, NMR, all of that. But that's later on. But they all have a purpose. They all have a purpose. So this isn't a random shape. This is a specifically highly complex, organized shape. It has a very specific shape. And if you didn't work that out already, what I'm going to talk about next, a very specific 3D shape of a complex, so a very specific complex shape that's 3D as a protein. There can only be one thing, right? And that's enzymes, right? I'm going to talk about that next, right? Enzymes are what are why tertiary structure are quite important. Or at least understanding tertiary structure is quite important because of enzymes, right? I will get into that quickly, but if anyone wants, this is why I was going to talk about this more with the previous thing about the hair. So what I was talking about the hair was correct, but just on top of that as well, you now have so for example, black people's hair would have more disulfide bridges, more van valence molecular forces, hydrogen bonding, ionic interactions, and that's what causes this more curled shape, more complex shape. If you look at if you look at people's hair, black people know this, it's more curled. It's more curled, and that's the reason why for it. Whereas for Caucasian people's hair, it's more straight, and it's because obviously hydrogen bonding, but you have either less basically sheet, or less hydrogen bonding, less of these disulfide bridges, less of these van der hydrogen bonding ionic interactions, and that's why your hair is more straight and less curled up. Now, if you can have different hair products. Now, different hair products would then cause different bonds to happen, or increase more bonds or decrease more bonds, depending on what type of compounds that you're adding. But that's why understanding the structure is so important, not because of just hair. It's because of in the exam they'll give you a question that it doesn't sound like it makes sense, but it's about what testing is your understanding of the structure and why and how changing the structure, adding certain compounds could change the bonding, and changing the bonding changes the structure. That's how you should answer your questions. Changing, yeah, I've said it already. All right, enough talking. Now I'm gonna go straight into review. So we've learned so far. So protein structure. So we have the three types of proteins. So three types of structure. So primary, and we know from primary is just a sequence of amino acids. And then we have the secondary structure, which is just either beta pleated sheets or an alpha helix. and then the most complex one of them all, the tertiary structure. And that's just the overall 3D shape. Alright, cool. So as I said before, enzymes are, if you're talking about just tertiary structure, the main example of tertiary structure is with enzymes, right? So one of the most important functions of proteins is their use as enzymes. So enzymes are biological catalysts which are highly specific. You should know this by now, but specificity. So enzymes are made specific by their selective active site. So the tertiary structure, so active sites, so first of all, enzymes have active sites. So people that don't really specialize too much on biology, I mean, you should know about active sites at least, but yeah, enzymes are made by their selective active sites, and the active site the active site on an enzyme has a specific tertiary structure that is complementary to the substrate, and that because it has a specific tertiary structure, active site on the enzyme, which is a protein, that's what allows it, and that's because it's sorry, I'm getting my words muddled up here. Enzymes have a specific tertiary structure active site which is complementary to the substrate, and that allows ES complexes to form. But they're so specific that they can even select between stereoisomers. So we know about stereoisomers, right? Which are different. The stereoisomers are compounds that have the same structure formula but different arrangement of atoms in space. So they look pretty much, they can be non-superimposable images. We already know that already, but the one thing we know about stereoisomers, they look very similar. They look very, very similar, but because enzymes are so enzymes active sites are so specific, and they're so their test structure is so specific. It's only complementary to that one substrate only, and it's so specific that they can select between stereoisomers that they will only bind to one enantiomer of a substrate. So if there's two types of enantiomers to that substrate, it'll bind to only that one. It won't get confused. It won't, I say get confused, but it won't be similar to the other one. It will be specific only to that enantiomer of a substrate. So for example, an example is L-amino oxidase, which only works on the L-amino acid and not on the other enantiomer, which is the D-amino acid. Enzyme action, right? So a simple representation of enzyme action is the lock and key mechanism, but in biology, the understanding of enzymes is the induced fit model. But that's a bit more. Well, you should know this by now for GCSE, but explaining this method can be a bit more. I don't want to confuse too many people about how to explain that part there, but yeah, if everyone knows about induced fit model, is kind of like how it molds itself, so it binds first and then it changes shape to make it more complementary as it binds to it. But don't worry about that. Just think about the lock and key mechanism. So a key, which is the kind of acts as the enzyme's active site, with the part of the key is the enzyme. The specific part of the key that bind to the lock is like the active site, and then the locks the specific part on the lock where that part of the key will bind to is the substrate, where the substrate is, where the active site will bind to the substrate, the binding site of the substrate, you could say, right? So that's how we want to think about it. So this shows a simple representation of the importance of the shape of the active site, because if it wasn't specific, it wouldn't bind to it. No ES complex is formed. Because enzymes are proteins, this shape is determined by the 3D structure of the protein. Here we go. So drugs and inhibitors. So enzymes can be deactivated using drugs called inhibitors, of which there are two so there's two types of inhibitors, competitive and non-competitive. Now I don't know if you need to know the difference between non-competitive and competitive inhibitors for A-level chemistry. I know you definitely need to know it for biology. You definitely need to know it for biology. I don't think you need to know it for chemistry. Leave if you really want me to explain it, just leave a comment in the description, and I'll go through it. But because it's not a very difficult thing to go through. Could I even explain it now? No, I'm not gonna comment. People don't know about the allosteric site. Yeah, so I'm not gonna go through it. It's mostly a biology thing. But yeah, if people really want to know, but just leave a comment in the description and I'll explain it. But the level of inhibition is dependent on the relative. So what things you need to know about inhibitors is that the level of inhibition is dependent on the relative concentration of the substrate and drug, and the relative binding strength of the drug and the substrate. So concentration of the substrate and drug, and the binding strength of the drug and the substrate. Those two things need to know. Mostly, it's mostly this one. If I'm being honest, it's mostly this one here. If I'm being really honest, but that is quite important as well. And at least when you go into year 2 transition metals and you start learning a bit more how these structures, how enzymes, how catalysts work, you get to understand this second point a bit more. But most of the questions are looking for that first point. The last one here is about using computers to design drugs. So this last one here is more to do with how to analyze, how to know how to identify certain proteins. Now when I say computers, there's two methods really that it's talking about, and it's talking that you will get to learn towards the end of organic chemistry, and that's chromatography. First with NMR and infrared. Infrared you should have covered it in year 1. But NMR is something that you'll get to learn more about. There are other methods, of course, that more advanced pharmaceutical scientists would be able to tell you about. But for the ones that you need to know for A level, you're not going to be actually doing the most complex things, but you need to know about NMR and different types of ways of identifying proteins in particular. But that's another video, that's another time. I'm not going to confuse you too much. I'm just going to say here that using computers to design drugs, my former teacher was a pharmaceutical lab worker. I don't know how to call it. He worked in research, and he did this. He used computers to design drugs. Because if we know the structure of the enzyme and its active site, chemists can use the computer modeling to find new drugs that would fit into the active site. So if you know what the active site of an enzyme looks like, and you wanted to, let's say, inhibit it, or promote binding, right? You then create a drug that has a complementary tertiary structure to that enzyme's active site, and you do that using computer modeling. And the modeling calculates whether or not the molecules have the correct polarity, stereochemistry to fit into the active site. Now, you don't need to know. You don't need to know the specific parts of this point. I just put it here so people can understand. This part is just, but you all need to know here is that you can use computers to design drugs. It's not, you don't need to go specifically into these points here. The proposed models are then synthesized and the structures optimized by experimental work. Yeah, but it's just understanding here that computers are used to design drugs. Now, before I go on to move on from here, right? The reason why I try to make it clear about the active site has a specific tertiary structure, because this is about tertiary structure, right? It's because the one thing I didn't mention here about enzyme action is if they're denatured. So if enzymes, we know we work in specific conditions, things that can break that bonds are if it's if we add too much acid, if the enzyme is put in a very acidic or very basic solution, it causes it to be denatured. Biologists know this as denaturation. What's happening here is that you're breaking you're breaking these bonds here. You're breaking these disulfide bridges, the weak van Valentine forces, hydrogen bonding, ionic interactions. And when you break those bonds, like I said before when I was talking about this being like a rope, right? If I snap one of these ropes, let's say I have multiple ropes here all in a certain way, but if I snap one of these ropes, it's gonna go like this, right? There's nothing holding it back, so it will just go back to its original shape. If I break another one, that's what you're doing when you're adding in acidics in a acidic solution. That's what denaturation is, just breaking the tertiary structure bonds. So when now you've broken some of these bonds, you've now changed the tertiary structure. Now you've broken more bonds, and now it's going back to like something like this, right? Not doesn't have to be as drastic as that, but the point being that you've now broken so many. First, we'll mention that your denaturation, you're breaking down certain bonds in the tertiary structure to the point now where you've changed the tertiary structure of the active site so much because you've broken so many of those bonds that it's now no longer complementary to the substrate and incapable of being able to form an ES complex. I kind of sound like I'm going too much into biology here, but about the most important here is that what denaturation is, why it affects the structure, and if you break in structure, now the tertiary structure is no longer specific. It's not specific anymore, and therefore no ES complexes can form. But that's it. And now just a quick recap on secondary structures. There's two proteins. There are two protein secondary structures, and both of them are held in place by hydrogen bonds. So hydrogen bonds, both secondary structures are held together by strong hydrogen bonds. The positioning of these bonds forces them to make the shapes that they do. So base pleated sheets. So base pleated sheets take the shape similar to folded linen. So they're similar to folded linen sheets that you might make of your bed, right? As the name suggests, pleated sheets. They're like sheets. Just think about them like that. They're I'm sure if I could measure the angle right, they'll be both perpendicular to one another. So perpendicular, no, parallel. So not perpendicular. Perpendicular is not, that's right angle. Sorry, they'll be both parallel to one another. Don't say perpendicular. That's wrong. Sorry, they will be parallel to one another when they form the hydrogen bonds. The two strands will be parallel to one another all the time. So that's what you have to think about. An alpha helix structure is more like a coil. So much like a spring on a slinky. That's what, imagine like a slinky. Or imagine if, I'm not going to use black people's hair as an example, but it's, you can see that black people's hair kind of looks like an alpha helix. It kind of like a coil structure. But if you think about car suspension or a slinky, that is what an alpha helix looks like. It's a coil. Alright, so hopefully this video is helpful. Hopefully I didn't make you more confused. If I made you more confused, please leave a comment so I can try and make this videos helpful. But that's it. That's what I have to say now.